Somewhere out in the universe, a black hole the size of a small galaxy's heart is moving across space at 2.2 million miles per hour. It is not drifting. It is plowing through interstellar gas like a ship through water, leaving a wake of displaced matter behind it at hundreds of kilometers per second. The James Webb Space Telescope caught it in 2025. It is the first runaway supermassive black hole ever confirmed, and the forces required to throw it are, in the language of the astronomer who found it, Peter van Dokkum of Yale University, almost beyond what the field can account for. Supermassive black holes sit at the centers of nearly every large galaxy in the known universe. They anchor everything around them. Pulling one out of place is not supposed to be possible. And yet, here is one moving. This is a story about black holes, and more specifically about how the James Webb Space Telescope spent a single year overturning much of what we thought we understood about them. The basic physics has been settled for over a century. A black hole is what general relativity, the theory Einstein published in 1915, predicted would happen if enough matter were crushed into a small enough space. Carl Schwarzschild solved Einstein's equations a year later and identified the boundary called the event horizon. The event horizon is not a wall or a surface. It is a one-way membrane in the geometry of space-time. Cross it, and there is no path that leads outward. Every direction becomes inward. At the center is what physicists call a singularity, a point of theoretically infinite density where the equations of general relativity stop making sense. Quantum mechanics says infinite density should not exist. General relativity says it should. Both theories work brilliantly on their own, and they have never been reconciled at the place where they meet, which happens to be inside every black hole. This remains one of the deepest unsolved problems in modern physics. If you fell toward a small black hole, the difference in gravity between your feet and your head would stretch you into a thin column of matter long before you reached the boundary. Stephen Hawking gave this process a name in his book A Brief History of Time. He called it spaghettification. Near a supermassive black hole, the tidal forces are gentler, and you would cross the event horizon intact. From the outside, anyone watching you fall would see you slow down as you approach the boundary, your image stretching, reddening, and eventually freezing in place. Because time itself runs slower in stronger gravity. This is not a metaphor, it is a measurable effect, confirmed in laboratory experiments and one of the strangest predictions general relativity ever made. In 1974, Hawking proposed that black holes are not entirely black. Quantum effects at the event horizon should cause them to emit a faint thermal radiation, slowly evaporating over unimaginable spans of time. A black hole the mass of a typical star would take roughly 10 to the power of 67 years to disappear. The universe itself has only existed for about 13.8 billion. Hawking radiation has never been directly observed, but if the prediction is correct, even black holes are temporary. For most of human history, none of this was anything more than mathematics. We had no image of a black hole and no proof they existed in the form general relativity described. On the 10th of April, 2019, the Event Horizon Telescope collaboration released the first photograph ever taken of one. It was the supermassive black hole at the center of galaxy M87, roughly 6.5 billion solar masses, 55 million light-years from Earth. 3 years later, in May 2022, the same collaboration released an image of the supermassive black hole at the center of our own galaxy, Sagittarius A star, roughly 4.3 million times the mass of the Sun, 26,000 light-years from Earth. These objects are real, they are everywhere, and nearly every large galaxy has one at its center, including ours. Until recently, the question of how they grew so large had a fairly settled answer. A large star runs out of fuel, collapses, and leaves behind a black hole of perhaps a few times the mass of the Sun. Over hundreds of millions of years, these small black holes feed on surrounding gas, fall toward the centers of galaxies, and merge with each other, slowly assembling into the supermassive objects we see today. This is called the light seeds theory. It worked for a long time. Then the James Webb Space Telescope began looking at the early universe, and the math stopped working. In November 2025, a team led by Roberta Tripodi of the University of Ljubljana published a paper in Nature Communications describing a galaxy called Canucks LRD Z8.6. The galaxy is small and faint and belongs to a strange new class of objects nicknamed little red dots, which Webb has been finding in surprising abundance. Inside it, the telescope's near-infrared spectrograph identified an actively growing supermassive black hole. The galaxy existed only 570 million years after the Big Bang. The black hole was already enormous. And in the language of the field, overmassive, meaning it was far larger than its host galaxy should have been able to produce in the time available. According to Tripodi, the black hole was growing far faster than anything in the standard model could explain. This is not an isolated case. A black hole called UHZ1, detected by combining data from the Chandra X-ray Observatory and Webb, appears to have existed just 470 million years after the Big Bang, with a mass of roughly 10 million times that of the Sun. There is, mathematically, not enough time in the early universe for a stellar black hole to grow that large that fast through the standard merger process. Something else must have happened. That something else may be the heavy seeds theory. Instead of starting small and growing slowly, a giant black hole forms in a single event, directly from the collapse of a vast cloud of gas with no star required. A black hole of perhaps 1 million solar masses, born already enormous. Until 2025, this was a theoretical possibility on the edge of the field. Then Webb found the Infinity Galaxy. Peter van Dokkum and Gabriel Brammer of the University of Copenhagen were going through images from the Cosmos Web survey when they noticed an unusual object. A galaxy with 2 compact red nuclei, each surrounded by a ring, the whole structure resembling the symbol for infinity. Sitting between the 2 nuclei, embedded in a vast cloud of ionized hydrogen, was an actively growing supermassive black hole of roughly 1 million solar masses. It was not at the center of either galaxy. It was not at the center of any old stellar core. It was floating in the gas. As Van Dokkum put it, everything about this galaxy is unusual. X-ray emission detected by Chandra and radio emission picked up by the Very Large Array confirmed that the black hole is actively feeding. Its position, alone in the middle of a hydrogen cloud, is the strongest observational evidence yet that supermassive black holes might form sometimes simply by collapsing out of gas, born in a single moment, fully formed without ever having been a star. In December of 2025, a team using Webb's mid-infrared instrument turned toward an ancient galaxy nicknamed Virgil. In ultraviolet and optical light, the kind of light Hubble can see, Virgil looked perfectly ordinary, a small, quiet, star-forming galaxy. When the team looked at it in infrared, an entirely different object appeared. At its center, hidden from every previous telescope, was a supermassive black hole, another overmassive one, far larger than the host galaxy should be able to support. The team described Virgil as a Jekyll and Hyde galaxy, quiet invisible light, a monster in infrared. The implication is that some of the most extreme objects in the universe may have been hiding from us this entire time, invisible to every telescope built before Webb, simply because we were not looking in the right wavelength. In the same month came the runaway, the supermassive black hole moving through the cosmic owl galaxies at 2.2 million miles per hour. Van Dokkum and his team caught it because of the wake. Webb detected gas being pushed sideways at hundreds of kilometers per second, a clean shock wave trailing behind something massive enough to displace everything in its path. According to Van Dokkum, the shock signatures are crystal clear, and there is no doubt about what is happening. A supermassive black hole has been thrown out of its home, almost certainly by the gravitational chaos of a previous galactic merger, and is now moving through deep space, leaving a scar across the cosmos behind it. 5 discoveries, 1 year, 1 telescope. What we know now is this: black holes exist. We have photographed them. They sit at the centers of nearly every large galaxy. They bend light, dilate time, and devour matter. They obey the equations Einstein wrote down more than a century ago, and those equations stop working at the singularity inside them. Gravitational waves from merging black holes have been detected directly, an achievement that won the 2017 Nobel Prize in Physics. Thanks to Webb, we now know that supermassive black holes existed earlier in cosmic history than our models predicted. Some appear to grow faster than their galaxies. Some are hidden from optical telescopes. Some somehow can be flung across space. What we do not know is larger. We do not know what is inside a black hole. We do not know what happens to information that falls into one, a question Hawking himself raised and never fully answered, and which remains one of the deepest puzzles in theoretical physics. We do not know whether direct collapse is the rule or the exception in the early universe. We do not know how many overmassive black holes are hiding in galaxies that look ordinary in the only light we have ever bothered to check. We do not know what threw the cosmic owl black hole, only that the forces involved must have been extraordinary. For most of the last century, black holes were the strangest things our equations could produce. They are now the strangest things our telescopes can see. The universe is not running on the model we wrote down. It is running on something we are only beginning to read, and the instrument that is reading it has been operating for less than 4 years.